In the previous video, we used system identification to obtain the model parameters. Today, we will explain why we should use a model-based controller, and how to use a model-based PID controller to control a motor. This is your control theory teaching assistant. There are two main categories of controller algorithms: model-free controller and model-based controller. Model-free controller is usually PID controller, which reach the desired response by manually tuning the Kp, Ki, and Kd parameters. The advantages are simplicity and ease of use. However, the drawback is that tuning the parameters might take much time. Here are many types of model-based controllers, such as PID, LQR, LQG, and sliding mode control, which reach the desired response by adjusting bandwidth or weighting. The advantages are reducing the difficulty of parameter tuning and allowing for the simulation of potential response. The drawback is that it requires a system model and parameters, meaning that system identification must be done. The above points are mentioned in most tutorial videos. Therefore, today I will discuss another advantage of model-based controllers, which is proceduralization. Imagine if you were an ordinary person with no concept of control theory, not even having heard of PID. But you could still use a motor driver's tuning program to reach the desired response on your equipment. For example, servo motor tuning programs usually ask the user to set the upper and lower boundaries of movement. The motor will then move back and forth for a while. Go to the next page and set the desired rigidity. Once that's done, you can send commands for the motor to quickly move to the desired position. Having the motor move back and forth is performing system identification. Setting the rigidity actually means that the motor is controlled by a model-based controller. Today, I will teach you how to use a model-based PID, so that you can control the motor by simply setting the bandwidth. The inner loop uses PI controller to control the speed. The outer loop uses P controller to control the position. For position control loop, the desired position is subtracted from the measured position, and multiplies this difference by Kp to output the desired speed. For speed control loop, the desired speed is subtracted from the measured speed, and the speed difference is processed by the PI controller, where the difference is multiplied by Kp, and the integral of the speed difference multiplied by Ki. Both are summed. This results in the output voltage for the motor. Since we are using a model-based PID this time, there is no need to tune the PID gains through trial and error. When the motor model and parameters are known, we can define the position control bandwidth to be omega position. Then the Kp in the position control loop will be omega position divided by 2, and the omega velocity will be twice omega position. For speed control, the Kp will be omega velocity divided by b, and Ki will be a divided by b multiplied by omega velocity. The biggest advantage of this control architecture is that you can directly obtain the PID gains by simply adjusting the bandwidth. Additionally, the bandwidth can be replaced with other more easily understood terms, such as rigidity or convergence speed, making it easier for ordinary people to quickly understand how to adjust. This video explained why a model-based controller is needed, and how to use a model-based PID to control a motor. The next video will teach how to implement. See you next time.